Again, I'm Gavin McQuillan. I'm from Urban Airship. I'm on the data engineering team. We count stuff, basically, mostly in Hbase. So we are a mobile messaging company at Urban Airship, so we do a lot of things like there's hundreds of millions of devices sending us events. We're counting events. Sometimes we're uniquing them, but not always. It's often like number of app opens, things like that. Things that are related to a push message that went out. We need to sort of correlate and count all kinds of data that are coming in at a very high rate. So it's a big task, and we use Hbase. We leverage Hbase, which is quite good at that. But when you want to like store things or sort of look things up by dimensions, you want to be able to say like, okay, I want to know about people who are in this cohort or in this geography. You want to be able to like add those dimensions to Hbase, and so we do that through a homegrown system called DataCube, which is our kind of OLAP solution for this. The problem though is that that is very, very, very problematic in terms of adding new features. It takes a lot. You have to basically write code every time you want to add a new dimension. Changing old dimensions or changing your schema, which is again just how we're creating these key encodings, is actually pretty difficult. So very time intensive. You have to rewrite your whole database basically when you do that. So we'll talk about how that problem statement, how we solve that with Postgres. We need distributed Postgres. We'll talk about how we do that. Probabilistic data structures become integral for basic error correction in a distributed Postgres in this particular experiment that I ran. And benchmarking and sort of what it looks like as a loaded and unloaded cluster of Postgres nodes. Again, our problem, kind of talked about this a little bit, but one of them is also data consistency. Since in Hbase you have this distributed column store, you have no notion of locking rows. So if you're doing denormalized aggregations, where some are components of another, you actually have no way of making sure that that's consistent. So you have totals and sums that are actually potentially coming, that are potentially out of sync, and that's a problem. People will notice these sorts of things. Again, adding new dimensions and changing the schemas is very difficult. There's the possibility for double counting, and it's very difficult. Since these are just roll-ups, it's very difficult to go back and fix those sorts of things. And there's no particularly good way of doing consistent backups. We mostly just replay events when we have a situation where we need to do that. Whereas in Postgres, you don't have that problem as much. You can basically have a point-in-time snapshot. So we're exploring solutions for how to make that better. How do we get those features that we want and sort of alleviate some of the problems we have with Hbase, but still getting this high write throughput. Again, we have not a lot of need to do a lot of reads, but we have to do a lot of write throughput for the kind of traffic patterns that we have. And it would also be nice to be able to do ad hoc queries. We can't really do that with Hbase. You want to query the data, it's write code. And then we have well-known and replication and backup story with Postgres. So it means that like your operations team's not going to sort of be like, what, another database? This is ridiculous, you know, and they do that sometimes. But there are some problems with Postgres, and that is that it's explicitly not well known for being a really high write throughput database. And that it can be operationally complex if you do these sort of distributed types of scenarios with Postgres. And so I chose using PLProxy for its simple API. It was developed at Skype, and they use it pretty extensively for sort of for fanning out their writes and sort of taking different particular types of data and using one database. You can actually access your accounting system. You can access all of your user databases. Your message systems can all be run through PLProxy, which is foreign data wrappers written in PL SQL. It's extremely flexible because they're just functions that are running on other databases. You can use as far as I know, it's compatible with pretty much every other extension. And you can upgrade Postgres pretty easily and not have to worry about it because, again, the functions, the core of the system are all just PL SQL. And so the approach here to sort of get our consistent data in a distributed Postgres system is that you can look at doing two-phase commits, or you can use some sort of commutative idempotent data. And we chose to go with the latter one because two-phase commit is slow, and that would basically kind of defeat the purpose of this experiment. So we use the Postgres-HLL extension, and if you went to Andres's and Marco's tutorial, they talked about that pretty in depth. And I'll talk a little bit about how HLL works if you've never heard of it, or if you're you only have kind of a rudimentary understanding of how it works. But the more important thing to understand is that it's commutative, which means it doesn't matter what order you apply your additions, basically. And it's idempotent, so you can apply them over and over again without any problems. And this is critical in this particular experiment for data consistency, because we'll talk about it in a little bit, but it's also nice because if you want to, you can go back and replay data and not worry about double counting. So it alleviates two problems in one there. And then it's fast but approximate cardinality counts. Some of our counts need to be like cardinal, like we need to know the total number of unique items in a set, but not all of them need to be. So there's some sort of equivocations we have to make about that. And this is really dark, I apologize for this. HLLs basically work where you take a stream of, in our case, it's usually strings, but you run it through a hash function to really increase its entropy as much as possible. So I think the Postgres-HLL extension ships with Murmur 3, which is supposed to be a very good hashing function. And basically what happens is you take that hash function, and then the prefix of the hash ends up telling you what bucket. So you have these different buckets here, and all this is definable, but you usually have thousands of buckets, and this is the state you're storing in Postgres. And the prefix of the hash tells you which bucket to put the rest of it in, and then you do a sort of a mask to do that, and then you sort of shift your bits into that bucket, and that's pretty much all you do for a write. Now for a read, when you actually want to get some data out of it, because not just have a bitmap sitting here on disk, but why it's called HyperLogLog is that you take the log of the harmonic average of the highest number of consecutive zeros in binary for each of these buckets. And then you multiply that by the number of buckets, and then you multiply it by a magic constant, and then you will get a very close approximation of the unique items in the set. And so that's my one slide talk about it. You could do an entire talk about this algorithm if you wanted to, but we're just going to, this is just sort of a brief overview of how it works. And if anyone's curious, the magic constant is I think it's 0.714, 0.713, something like that. And that just happens to be a constant. When you multiply it by the result of everything else you've done, you happen to get a better error margin. So anyway, so now PLProxy. So now we know a little bit about our probabilistic data structure that's going to allow us to safely use a bunch of shards that don't have transactional boundaries that are shared. What does PLProxy look like? Well, you basically, the two pieces are you have to set up the cluster config, and that tells you about partitions, which databases are on which servers, and that's just a function that returns that value. And then connection information, like how long does your connection pool live, and things like that. And a partition mapping looks kind of like this. You have create server. Server is a keyword for PLProxy. It's a foreign data wrapper, of course. We talk about our connection lifetime, and here's our actual mapping. This is a PLProxy ID, and it talks about each of the actual database name and the host name that it's connected to. And then we sort of set what the visibility is for users or roles on that system. And then a function. It pretty much looks like any other function. It has your input parameters as a return type. It specifies the language, which is PLProxy, which is important to remember. And then you have to identify a cluster. And then this run on tells you specifically which shard you want to run this one on. So you want to run it on the shard that has the sort of range of hash of whatever the event is that you're going. So it should only go to one shard who owns the hash of whatever this event you just hashed. Sort of like a Cassandra, if you're familiar with Cassandra, how there's a sort of a token ring. It's sort of like that, or memcache, actually. There's other options for run, though. You can run on all. You can run on one, just any one at random. So there's a bunch of options for that. But basically, these keywords here, these functions that PLProxy brings to the table that you kind of need to know about are connect, and that explains how the cluster itself is created and what the connection pools look like. And we kind of elided that. We don't need to worry about that too much. The cluster is sort of which tables are you distributed. So all that's defined in your cluster. The split basically tells you if you have parameters that are arrays, you can tell it to split those up, and it will actually take like one item off the top of each array and pass that as like one tuple to a specific function on a specific server. And then run is kind of what we described. We just talked about that a little bit before. But target's interesting because you can actually change the name. By default, when you just say run on a PLProxy function, it will call the equivalent named function on that remote server that it's configured to talk to. So if you change it, if you need to change it and say like, I have proxy upsert counts, but I want to run upsert counts on the remote, you would say target is upsert counts. So that's how you'd sort of change the name of the function that you're actually calling remotely. So we have an experiment to sort of determine like whether or not this is a feasible system to replace Hbase. And also I'll take questions at the end just to save time because we're running low already. So we had 3 Dell nodes that are pretty fast. The initial simple topology, just sort of like just testing out what it looks like to use PLProxy. We only have 2 data shards and 1 proxy shard. We have a really simple table here with an ID, a date, an hour, event IDs, and that's our HLL there. Category is just some sort of text that we'll want to be able to filter or group by later. This is just an upsert, and unfortunately it's really messy, and I elided a lot of information that wasn't related to the HLL data type. And pretty much it's going to be hard to read, so I'm going to skip it. But basically, this is an upsert that uses HLLs on that table, and that's on each of the data shards. So a single write looks like this. You specify the types that you want to, or your input parameters. And here, notice that it's a string. It's not an HLL type. That's what the upsert function handles for you. And then we did some tuning. We looked at, we basically ended up with an index on 3/4 of the columns. Specified a high fill factor, all the memory best practices, that kind of stuff. We're not going to talk about that too much. And we were getting about 2,000 events a second on these 3 nodes, which is, it's respectable, but it's definitely not competing with Hbase, where we're kind of need to be talking about hundreds of thousands of events a second. And events here are tuples, effectively. So batching is an obvious next choice, and again, that split function that we have with PLProxy. Then the PLProxy language allows us to basically, you can specify huge batches and it will intelligently split up and collate those correctly and send those batches of data to individual shards. So we have equal numbers of parameters in our IDs, dates, hours, events, and categories, and those will basically get cut up correctly and run on each of the shards. And then, so that, it's basically, this is what you see when you have a batch query. You're basically setting it into arrays. So this doesn't look very SQL-y, and that's true. But in our use case, this will probably be a streaming infrastructure that's writing these queries, and the batches will be thousands, or hundreds or thousands of tuples at a time. So that's fine. It's going to be machine generated anyway. And so just to visualize what a PLProxy transaction looks like. So you're the client here, and you're submitting this transaction 1 here, and you go into the proxy, and you have these 3 IDs, but 2 of them are actually for the same row, but whatever, you're just incrementing, right? So 2 of them go to one partition and 1 go to the other, and they all succeed on those partitions because PLProxy works in auto commit by default. So what happens is it runs your statement and commits it if it succeeds. If all of those succeed, then your parent transaction that you have with the proxy node that you came in will succeed. So that's cool. But when things go wrong, if anything goes wrong, actually, if any transaction aborts on any of the partitions, so even if you have hundreds, if any one of them fails, your parent transaction will fail. But that doesn't mean that they don't succeed on other partitions. So you have to, this is where being able to replay your data is really important. And so, for example, because of the way we're doing splits, and we don't have any sorted data in our batches, it's very possible to get deadlocks, for example, where transaction 1's holding a row that transaction 2 needs, and transaction 2 is holding a row that transaction 1 needs on the same partition. You will get a deadlock, and you will have a bad time. So basically, you can sort the tuples before you submit them, which seemed arduous. So we instead opted to work with a single writer pattern for the purposes of testing. And so now with batching, we got up to 11K a second with our simple topology, which is really only 2 nodes that are writing data. And so with 200,000 events, and these are sort of various batch sizes, in our simple topology here, We've got a batch size of 1,000, 2,000, 4,000, 8,000, and we get up to about 11,000 events a second before it sort of starts to plateau. So then the next thing that's obvious is, okay, well, we can really increase parallelization, and in fact, we should probably reach for as many cores as there are on these 3 systems. And so this doesn't even quite do that, but you'll see that the results here are that we get quite a bit more throughput. And so these are insert-heavy, 2 million events in a test, and with a batch size of 4,000 and 8,000, and we're getting around 25,000 events a second. And so if comparing both of them, in both cases now using 2 million events in each test, you see that the advanced topology is quite a bit faster. And unfortunately, I don't have good quantitative data on how the number of CPUs really impacts the number of or the amount of throughput as you increase the CPUs. But I imagine it's roughly a doubling of CPUs will increase by 150%. So it's something it's pretty interesting. But we care about what this looks like on a loaded cluster. So these are all fresh machines, right? So we deleted the data between all those tests. So here we have a loaded system with 60 gigabytes of test data, 20 gigs of indexes. We add in this testing 20 more gigs of data and 6 more gigabytes of indexes. And we set up concurrent requests by basically running all these inserts in 10 different screens kind of at the same time. So they take many minutes to run all these data, but we get a pretty good approximation of kind of what production traffic looks like. And so even loaded here, we have we did sort of an insert heavy route where it's this is all new data, so it has to sort of create those new rows for every single one of them. And then in the update heavy approach, it's quite a bit faster, and that's probably, and basically we're just running the same test again since our data is idempotent. Everything, once it's already been saved once, you run it again, it's just going to be an update. And it's idempotent, so data doesn't really change, but we still see, we'll still sort of see what an approximation of what it looks like for high update loads. And so here's one of the things that's nice is that we can actually do ad hoc queries now. We have this function called dynamic query that is on all of the data shards. And what I'm doing here is I'm passing a string that is actually the query I want to run on that shard. So that will run on each shard, and then we'll get merged back together on the actual the actual proxy node that I emitted this request from. And then once you get that, you're going to get basically a table back, and you can do anything you want. You can order, you can limit, that sort of thing. But the main caveat to worry about here is that it will materialize everything that is sent back from all of the shards. So if you do a select star from table and you do that on all the shards, you will definitely run out of memory on the proxy database that you emitted that. So you got to be careful. And so these are sort of the results of what we see. So we've ordered our data. We have our ID and our date and our hour and our cardinality count. And so I hope this hasn't been too fast, but we started quite a bit late. We've got about 3 minutes. So the wrap up is that I think that this is a totally feasible system. Using Postgres, rather, is a feasible system, a better replacement, actually, than doing kind of OLAP and HBase. We've tried it, and it's difficult to sort of maintain over the long term. Adding a new feature is as easy as a new group by, typically, because again we're using SQL. So you have to be wary of all of the nuances of distributed systems, but you still get to retain things like DDLs and the ability to have a schema that makes sense, and you can have constraints. However, these systems make Postgres, which is already it's not the easiest thing in the world to deploy. It has a lot of sort of caveats, especially with replication. It makes that a lot worse. It's a lot more complicated when you have a distributed system for it. So there's a lot of work remaining around that. We don't have cross-table joins unless you're joining exclusively on the key that is the partition key between tables, and it has to be the same partition key. Automated failovers and automated backup setup, none of that stuff is done in this particular system. And it would be really nice to integrate with PG Bouncer, which does connection pooling. You can do really sophisticated stuff where you sort of pause transactions temporarily, and it will fill a buffer while you're say doing some sort of failover or adding a new shard, say. So you can do some pretty sophisticated stuff there. And work is ongoing. This slide presentation, as well as a full like Ansible automation setup for making a test cluster of arbitrarily large size, and like some sort of actual test data generation. This is all on this URL, and these slides will be available. I'll make sure that those get out. And thanks. And it looks like we've got. Oh yeah, okay. And I'm sure pull requests welcome. I'm sure that there's some weirdness going on. This is my first time using Ansible, so. But it mostly seems to work. And I have some references at the end if people are interested when the slides are up. You can check those out. Are there any questions? We've got about a minute. Okay, that's interesting. Yeah, and so in the test setup where I had all the data that were in the graphs came from, that was all manual. It was horrible. So I have since worked on using Ansible to automate that in system. And what I've done is I've made every single data node also a proxy node for just the consistency. And that's where like having that target so you don't have any conflicts in the function names. You could also use schemas if you wanted to. That would be a good idea. So that's how I manage it. But that's a good question. It's kind of messy, so as much as possible, I try to keep everything the same on all the nodes. Basically, is my answer to that. And also automate it, because yeah, PLProxy is nice and everything. It's neat that you can extend the functionality of Postgres in SQL in a nice declarative format, but it is not the easiest to debug. It's not the easiest. I mean, there's documentation, but there's not a huge amount. So you end up doing a lot of experimentation. So. There was another question over here. Yes. So that was happening in the upsert. So on the actual shard, you're getting a string, and it goes, cool, I'm going to do the HLL hash, and then apply that to the type. Yeah, I definitely skipped over that. I thought I had far less time. If you want to, I could go back to that. No, it's like, in this case, for the most part, what we're doing is basically just setting state in that big bitmap. And what's cool about the Postgres-HLL extension that it's on GitHub, aggregate knowledge. I think that company's been acquired and is now called Newstar. Okay, huge fans of that extension. Yeah, okay. The really cool thing is that it's, depending on how you configure the buckets and different thresholds, is that it's an exact count for low numbers of thousands of events. So, and that's where people care about, like it's off by one, After that, it's people mostly care about, okay, what's the trend look like? I don't care, I want the magnitude and the direction, and I don't really care so much about the details as long as it's, it's close enough. And so for our purposes, I think that it's a really good match. Were there any other questions? Hi.
In your slides, there was a step where you mentioned there was some parallelization. That was not to go from sort of 11K to like 200K. What was that?
Not 200, 25. So basically, that was increasing the number of PL/SQL shards. So the initial mapping, really, there were only two. It was like each machine had its own database, and then the more advanced topology, and really what you'd want is probably a database per core for all the machines that you've got. Yeah, so that's definitely like would warrant more testing, for sure. Yes, Josh.
So how does the idempotency work with HLL? How do you ensure that the counts are idempotent?
Oh, I see what you're saying. Yeah, so the question's how do you ensure idempotency with HLLs? And the answer is largely I don't. That is kind of in the purview of the extension. These guys over here might be able to answer you better.
If you hash the same key, you should get the same hash.
Yeah.
And when you add the HLL, it'll set the same bits.
It's a deterministic. Yeah.
When you add it again, it doesn't change those bits.
Because yeah, I mean, so you take a hash of whatever the data is. That's a deterministic thing, and then which bucket you pick is also deterministic, and then the bit shift you do to sort of store those bitmaps into the buckets, it's always the same, right? Sorry? Oh, yeah, yeah, exactly. Yep. Yes.
On the hardware slide, that was like the initial.
Right, so yeah, right now in terms of like in production status, we're not using this in production because sort of priorities have shifted, but it's something we're still working on. So the next system we use, we do hope to, for this sort of high level rollup, we do hope to use HyperLogLog and Postgres to do that. And I think that this sort of experiment proves that even with something as simple as PLProxy, you're able to get those the numbers that you need to sort of be confident that you can do that in production and that you can grow. Cool. Did everyone get that GitHub? Yes.
So let me point out something about the HyperLogLog real quick.
Uh-huh.
It doesn't necessarily play nice with hash aggregate.
Oh, really?
So with very large cardinality, you can end up gobbling up all of your memory.
Okay, yeah. So but that's for...
And that's something that I'm going to be looking at. The 9.5, I believe, has the ability to say, give the size of the transition state for aggregates.
Uh-huh. Yeah.
I'm going to look at setting that because that seems to be the problem is that it says, oh, I'm going to do an aggregation of this.
Uh-huh.
And I don't know exactly how big my hash space is going to be.
Oh, I see, yeah.
You create it, and then you've got this 1, 2, 3K HLL.
Mm-hmm. Yeah.
You suck up all your memory.
Yeah, yeah. So, but I mean, so that's mostly a product of like how large your buckets are, right? How many bits you're storing in each bucket.
In a sense, it's just
Okay.
when you get a very large cardinality of
Mm-hmm.
your dimensions,
Yeah.
it says, okay, well, I'm going to estimate how big my hash map is going to be. And then when you actually throw data at it, it turns out that the hash map is much larger than it expected.
Oh, okay.
And so it has to do aggregates on every one of those hash entries, so it just keeps growing the table. And I know there's some work about memory bound hash ag.
Right. So, what would your recommendation be for sort of avoiding unbounded sort of unbounded like memory consumption?
I do is I try to keep it going through back rather than
Okay.
back.
Okay.
That's the disk. The other is to just try and keep the cardinality down.
Okay. Yeah, that's the other thing is that like the bounds for like cardinality counts for us, since they're usually bucketed by hour, are relatively low. No more than hundreds of thousands or millions usually. So for us, I think that isn't a large concern. But basically, the concern raised and the back and forth for those of you who are listening to the recording was that using a group aggregate is preferable to hash aggregates in certain cases with high cardinality in your set. Okay. Unless that's any other questions, I think that we are done.